Section 3.7, Assessing a Regression Model. Now, we spent pretty much all chapter talking about creating these lines of best fits and least squares regression lines, but we haven't stopped to talk about when it would be appropriate to do that. And to figure out if it's appropriate, we need to ask ourselves two main questions. The first is the relationship actually linear? Does it make sense to model them with a linear equation of a straight line, or is it actually curved? And in addition to that, if it is linear and we're going to use an equation of a straight line, how good is that equation when it comes to making predictions for the data? And we're going to tie this back to residuals. Again, residuals are the differences between the actual value that we get and the one that's predicted by the line of best fit. And a residual plot is just a new scatter plot that shows all of those residuals in a single display. So as an example, we have this scatter plot showing the cost of a 30-second commercial during the Super Bowl for the years 1967 to 2020. We can see this relationship is not linear. It's obviously curved here. However, they ran a line of best fit and created that equation. If we looked at the residual plot, the plot of all these residuals, it would look like this. The question we're trying to answer is, do we think a line of best fit actually fits this association? And in this case, it's pretty obvious that it doesn't, but sometimes it's not so clear. Right? A lot of times we'll see something, it looks like it's straight, right? And it's only when we look at the residual plot that we see that it's not straight. Right? And here's what we notice about this one. So all the points to start off are above the line of best fit. That's why in a residual plot, we see them, right, decreasing as it gets closer and closer to the line of best fit. Then we move into that middle section where all those points are below it. Okay, these ones are the smallest. We see them here. Okay, once we're at this point, we're the deepest part where the residuals are largest. All right, and then it gets closer back to that line of best fit before moving back above it. So this residual plot shows a pattern. Okay, if we see any kind of pattern in a residual plot, that's bad. It means that what we're looking at is not actually a straight line. Instead, what we want to see in a residual plot is a whole bunch of essentially nothing, just a bunch of scatter with no pattern at all. And we can see from looking at our scatter plot here of that Ford F-150 data that all of these points are plotted on this residual plot. It's these two here. The ones underneath it are the negative ones. Those are these two. Okay, we want pretty much an equal spread of points that are above the line of best fit and points that are below the line of best fit. Okay, so when we see a residual plot that looks like it's just scattered, it's not linear, it's not curved, there's no patterns there whatsoever, that's what we want in a residual plot. Put another way, when we create a line of best fit, we're trying to model the pattern. Okay, the actual equation is mapping out that movement like in the uphill direction or downhill direction. The residual plot should have no pattern left over. Okay, we don't want to see anything left in there, whether it's curved or linear, right? We just want it to look like scatter because the actual equation is the one that's mapping out that pattern. If we do see a pattern left over, there is a pattern, that's not an appropriate model. It's telling us that the scatter plot that we started with is not actually straight. There's problems with it. We don't want to make a line of best fit. If there's no leftover pattern, it means it is appropriate to go ahead and create a line of best fit. So to give a graphical representation of what I just described, here's our line of best fit on that Ford F-150 data. As it's moving down to the right, the points are moving down to the right with it. Okay, it's mapping out that association. The blue lines there are indicating the residuals. And if we were to make a residual plot, right, that red line moves horizontal, indicating a residual of 0. Okay, that's the same line. It's just telling us the distance from each of the points to the line. Right, the closer it is to the line, the closer that point was to the line of best fit. Okay, left over, there's no pattern. It's just showing us all these distances from those original points to that line of best fit. Another thing to look at when we're assessing a regression model is the standard deviation of the residuals. And this is exactly what it sounds like. Thinking back to chapter 1, standard deviation was average distance from the mean. Standard deviation of the residuals is just the average distance from the line of best fit. Okay, it's the size of a typical residual. So on average, how far are these points from a line of best fit? Here's our equation for it, and we calculated the same way we did standard deviation. 2 sections ago, we found the residual for a Ford F-150 with this mileage and this actual price. The residual was negative $4,765, indicating that it was less money than was expected for this car. All right, the point would be below the line of best fit. Here's the residuals for all 16 trucks in our sample. And if we wanted to find the standard deviation of these residuals, we square each of these values one at a time. We add them all up. We divide by n-2 in this case. This is the only difference when it comes to standard deviation. When we calculate a standard deviation, we divide it by n-1. Now we're dividing by n-2 for reasons that we don't really need to understand. But if you're curious, you can ask me in class and I'll be happy to explain it. As a last step, we square root it. We end up with a value of 5,740. And if we're asked to interpret this, we say something along the lines of the actual price of a Ford F-150 is typically about $5,740 away from the price predicted by the line of best fit. So in other words, these points on average are about $5,740 away from that line. The last thing that we're going to talk about when discussing how to assess a regression model is the coefficient of determination given by the variable r squared. And this is probably the most complicated of all the topics. To give a statistical definition of it, it measures the percent of variability in the response variable that is accounted for by our line of best fit. To explain what that actually means, let's talk about taking a guess as to what a random Ford F-150 costs. Now we have 16 in our sample and their prices vary quite a bit. If we wanted to take a guess as to what a random truck costs, our best, smartest answer would be the average, which is $27,834. Now, in actuality, that's probably not correct because all of these prices vary quite a bit. All right, the standard deviation is 9,570 because there's a number of factors that go into this, from the condition of the truck to the mileage to the features, etc. What we're doing with the regression equation is we're taking one of those variables and we're using it to help us give a better prediction about what a random Ford F-150 would cost. In this case, we're going to look at the mileage and we're going to use that to make a better prediction. So now, how much better is our prediction going to be once we know what the mileage is? That's what the r squared is going to tell us. The improvement of being able to make a guess about the price once we know how many miles have been driven. So let's backtrack a minute. And let's say we don't know anything about this truck. We're just being asked to guess the price. The smartest guess is the average. That's what this display is showing us. The difference between the actual price and our guess, which would always be the same at $27,834. All of these values have been squared. That's why they're represented as squares. If we add those all up, all right, this is the sum of the squares. This is how different we were, how wrong we were, squared. Now, if we know the mileage, we change this prediction line. It's not always going to be the same thing. It's going to depend on how many miles are driven. Right? So instead of that flat line, we have this diagonal line. Once we have that, the differences get a lot smaller. Okay? Again, they've been squared. When we add them all up, we see that we've improved quite a bit. It started at about 1.3 billion. With our new line, we're down at 460 million. The r squared is telling us how much did it improve as a percentage. Okay, so our difference decreased from 1.3 billion to 460 million. We always put it over that original larger number. We can see it decreased by 66%. So now, to put it into stat speak, the sum of squared residuals has been reduced by 66% when we were originally making our guesses based on an average, and we switched it to guesses based on how many miles have been driven. In other words, 66% of the variability in the price of a Ford F-150 is accounted for by the least squares regression line when we know how many miles that truck has been driven. It's not 100%. The leftover from this, the other 34%, is because there's other factors at play here. It's not just based on the miles that tells us how much this car is worth. There's things like the age of the car, the color, the condition, etc. So we went through a long process to get that R squared. Typically, it's not that complicated because if we know what the R value is, and in most cases we do, the R squared is exactly what it sounds like. It's just that value squared. To give one more example before wrapping up this chapter, we're back looking at that scatter plot of the soda cans that were shaken, tapped for a certain amount of time, and then opened to measure how much was left. The R squared was 0.85 and it's asking us to interpret this. Okay, we're always explaining the variability in the Y variable based on the model or the X variable. So in this case, 85% of the variability in the amount of soda remaining is accounted for by the least squares regression line when we know how long that soda has been tapped for.